Given an even-length array nums and a value limit. One move can replace any value with a number from 1 to limit, inclusive. A mirrored pair means nums at index I and nums at index n-1 - I, return the minimum moves so every mirrored pair has the same sum. In this example, the outside pair is 1 and 3, so its sum is 4. The inside pair is 2 and 4, so its sum is 6. The pair sums do not match yet. Choose target sum 6. Change the 1 into a 3, which is allowed because 3 is within the limit. Now both mirrored pairs sum to 6, using one move. So the output is 1. Second example, nums 1, 2, 1, 2, with limit 2. The outside pair and the inside pair both sum to 3 already, so no moves are needed and the output is 0. Before the intuition, assume you know the difference array pattern, mark the start and stop of a range update, then use a prefix sum to recover the values. Think of the final target sum as a signal. We do not know which target is best yet, so first we need to know the full range of target sums we are allowed to try. The smallest possible pair sum happens if both values are replaced with 1. That gives 1 plus 1, so the lower bound is 2. The largest possible pair sum happens if both values are replaced with limit. Here limit is 4, so the upper bound is 4 plus 4, which is 8. So every possible target sum lives from 2 through 2 times limit. In this example, that means targets 2 through 8. For one pair, each target falls into one of 3 settings: 0 moves, 1 move, or 2 moves. The 1 move range is a whole interval. For pair 1 and 3, the smallest 1 move target is 1 plus 1, and the largest 1 move target is 3 plus limit. Inside that range, the exact current sum gets one more improvement. At target 4, pair 1 and 3 already works, so the cost drops to 0. So the map for pair 1 and 3 is simple: outside the 1 move range costs 2, inside it costs 1, and the exact current sum costs 0. For pair 1 and 3, start with a cost array filled with 2's. Then apply -1 to the 1 move range, from target 2 through target 7. Apply -1 at target 2. Cost 2 becomes 1. Apply -1 at target 3. Cost 2 becomes 1. Apply -1 at target 4. For now, cost 2 becomes 1. Apply -1 at target 5. Cost 2 becomes 1. Apply -1 at target 6. Cost 2 becomes 1. Apply -1 at target 7. Cost 2 becomes 1. Now apply another -1 at the exact current sum. Target 4 is already 1 plus 3, so cost 1 becomes 0. For pair 2 and 4, the same idea applies faster: subtract 1 from targets 3 through 8, then subtract 1 more at target 6. This cell-by-cell work is exactly what the difference array avoids. The difference array marks only where each cost change starts and stops. Now write those same updates into one shared difference array. First pair 1 and 3 writes its baseline, 1 move range, and exact sum update. Pair 2 and 4 writes into the same difference array. After that, the diff array is complete for this example. Now sweep this completed difference array from target 2 to target 8. The running sum is the total number of moves for each target. The lowest running total is the answer. Now turn the idea into the solution. Build one shared difference array over target sums 2 through 8, with one extra slot at 9 for right plus 1 markers. Process pair 1 and 3. Here small is 1, large is 3, and the current sum is 4. Baseline cost is 2 moves for every target, so add 2 at target 2. Stop that baseline after target 8, so subtract 2 at the extra slot, target 9. Targets 2 through 7 need only 1 move, so subtract 1 at target 2. Stop that 1 move improvement after target 7, so add 1 at target 8. The exact sum is 4, so subtract 1 more at target 4. Stop the exact sum point update after target 4, so add 1 at target 5. Now process pair 2 and 4 into the same shared difference array. Here small is 2, large is 4, and the current sum is 6. Again, add 2 at target 2 for the baseline cost. Stop the baseline after target 8, so subtract 2 at target 9. The one move range starts at target 3, so subtract 1 there. That range reaches target 8, so add 1 at target 9. The exact current sum is 6, so subtract 1 at target 6. Stop that point update after target 6, so add 1 at target 7. After all pairs are written, sweep the difference array from left to right. The running sum gives the total moves for each target. At target 2, the running total becomes 3. At target 3, add -1, so the running total becomes 2. At target 4, add -1, so the running total becomes 1. At target 5, add 1, so the running total becomes 2. At target 6, add -1, so the running total becomes 1. At target 7, add 1, so the running total becomes 2. At target 8, add 1, so the running total becomes 3. The minimum total is 1 move, at target 4 or target 6. So the answer is 1. Time is O of n plus limit. We process each mirrored pair once, then sweep all possible target sums. Space is O of limit for the difference array over target sums. Define the main function with nums and limit. Let n be the length of the array. Create the difference array over all target sums, with one extra stop slot. Loop through the first half of the array, one mirrored pair at a time. Read the left value and its mirrored right value. Store the smaller and larger value for the one move range. The current sum is the 0 move target for this pair. Every target starts with cost 2, so add 2 over the full target range. Targets in the one move range improve by 1 move, so add -1 there. The exact current sum improves by 1 more move, so add -1 at that point. Prepare a running prefix sum and the best answer so far. Now sweep every possible target sum. Add the current diff value into the running total. Keep the smallest running total seen so far. Return that minimum as the answer. The helper applies one range update to the shared diff array. Add delta where the range starts. Subtract delta just after the range ends.